I'm recording. Okay, I'm recording the presentation, so I think we're ready to proceed. It looks like you're still sharing.
All right. So, hello, this is Majid Mantei from Virginia Tech, Blacksburg, Virginia. Thanks, Chris, for the introduction. Today, we're going to talk about electrical small antennas and different ways to transmit, receive broadband signal from these antennas. So, at the beginning, I would like to go through a little bit of history and then move forward with the electrical small antennas. Here I have an invention filed in 1887 by Granville Taylor Booth. So the idea was, if businessmen in the train, they want to transmit and receive telegraph, they don't have to get out of the train. They can do it on board. And you see that there are some coil on the road, and there's some coil in the train. And he basically filed this invention, and it was successfully working. Edison got really interested and tried to steal his invention. He sued him twice, and he lost. And eventually, actually, he sold it to Edison. Here we have another invention here again that basically Edison himself filed, and he basically raised the couplers, the inductor, to some height and tried to signal. And here we have another example that was 1884. William Priest. We have both Heaviside brothers, Arthur and Oliver. So Arthur was employee, what Oliver was consulting, so he was doing theoretical work behind the scene. So they made this really large coil here, loop like quarter mile each side, and very thick wire with the like big current. They were able to receive messages over a few miles. And then we basically, if you look at the time, we are in this is 1884. So, you know, Maxwell theories, Maxwell equations were already out there. But there were big resistance against his theory among the engineers and scientists at the time. Very few people that were believing in him. One of them was Heaviside was religiously believed in Maxwell, and we have basically in Germany we have the Hertz and his advisor, what was his name? Helmholtz. Helmholtz actually, he was his advisor. So Helmholtz assigned him basically an assignment. He was a student to practically show that Maxwell's equations work. And actually, he was not able to do that during the time that he was a student. Eventually, he became a professor, some other university. And in 1886, he started to do the experiments. And finally, he did it. And between 86 and 87, he filed it. So the idea here is there is a dipole antenna here. Let me change this to. There's a dipole antenna here, and it's connected to a transformer, where the one side of the transformer is connected to the battery with a switch. So when you turn the switch on, so the current, very strong current, goes to the first side of this transformer, very large voltage across this dipole. And when the voltage gets to the right amount, this spark happens into AB, and then large current goes through the dipole and radiates. So he has a loop at some distance, and he receives it. So if you remember that, if you pay attention, at that time, there was no way to generate or measure megahertz frequencies. So this was like between 150 megahertz at that range. So what he did, he made a loop resonance antenna. And the same way here, he put a spark gap here. He put a gap here, very smaller gap. So he had to make the room dark. And finally, he was able to observe that an electric structure can excite a magnetic system. Means we have electromagnetic. So he was the first one that proved that there is such a thing, an electromagnetic wave. The interesting thing about this invention here is, first of all, is using a transient part of the antenna. So it is not a steady state, it's transient. Second part is this electrically small antenna. So what basically I'm meant to say here was antenna theory started with the transient state and electrical small antenna. Here we have, of course, Tesla. In 91, he basically filed for his coil, a patent for his coil, and he filed many patents. Marconi uses patent for communication. And right now we are not doing sinusoidal. Sinusoidal got into the game when Alexanderson makes his alternative. I think he filed it in 1904. And then we have sinusoidal after that. There is another one that I would like to share with you. There's a patent filed with basically Oliver Lodge, Sir Oliver Lodge, in 1893. Again, this is a spark gap. But very interesting part of this invention, if you pay attention, we have a biconical antenna. And his invention, the text of the invention, is not focused on the biconical antenna. He's talking about this part. But actually, the major thing in his patent was a biconical antenna. And he didn't know that this is a big invention. So basically, this is the kind of like a very fast history of what I want to go through, transient state of electrically small antenna. Then we're going to talk about the how antenna radiates. We're going to talk about the radiation process here a little bit. So I have a dipole here, a static dipole plus and minus Q with some distance delta Z. And if I have an observation point, I want to calculate the field at that point. Basically, this is the potential and electric field when delta Z is very small, is going to be with approximately this equation that I have here. What I'm interested here is this part of the equation, which has r to the power of 3 in a denominator. So basically, electric field decays very fast when we go away from this to the power of 3. So then we have the field lines, and this is basically electrostatic. Now, I have a charge sitting at some point at rest, and a charge is going to accelerate for a short amount of time and then continue going at the steady state speed. So what I have here, look at this. So then I take a picture of this. After it moves away from this position, I take a picture. What you see here, there is a circle that I have here, that inside this circle, there is a time needs the wave to travel from the point to this circle. So it takes, with the speed of the light, so much time. After this circle, the field lines, they don't know that this charge has moved. So they are still in the old position. So what we see here, there is a disturbance on the field that travels with the speed of the light. And that disturbance has a theta component, if you look at it. And also has a minimum value in the both poles of this. So when I'm moving in this direction, I have a minimum disturbance in both sides of it, and I have maximum disturbance in the other side. So what I can show you here as an animation, basically, this is a very exaggerated animation. The speed of the light is very slow in comparison to the speed of the charge. And you see that this disturbance moves. That disturbance carries electromagnetic wave, and that disturbance decays 1 over r. We can show that. So what I have here, I have a charge and at rest, and I want to move the charge. There are a pair of charges, a positive, negative, and I want to make a dipole, and I'm going to spend some energy to make that dipole. Let's see how this thing happens. So when the charge gets away from each other, you see this is a solve of Maxwell's equations, shows there is some part that travels away, and then I have a static field here. If I play it again, you see that there is a positive red, and then there is a negative blue, and then that way with the red, blue, positive and negative goes away. So what I have here, I have a positive acceleration for charge when they start to move, and at the end I have a negative acceleration to stop. So if I look at the electric field with that motion that travels away has some sort of second derivative of the charge variation. I have another example that actually I have a two charge on top of each other. I move them away from each other. I'm gonna put them back together again. So this is different. So I'm coming up and then I go back to the point 0. So you see that this time, when the energy goes away, I don't have any energy left associated with this charge. Means when they're on top of each other, I don't have field and I don't have any effect of that motion around this area. That effect is gone. This is the part actually we want to use. It means that if I go one cycle of the oscillation, as I do here, and when I stop the oscillation, the field, the stored energy, everything, we don't have anything. Everything is radiated. We don't have anything else there. So the field goes to 0. This is the part that actually I'm interested in. I'm going to talk about it. Again, second derivative here. I have acceleration at this point. I have acceleration up here, and I have acceleration down here. So one maximum plus here, then negative acceleration here, and positive acceleration the other way. So I show that basically electric field is second derivative of charge variation. So here I have the dipole. The way that I scale this dimension, the dipole is oscillating at 300 megahertz, and the size of this box is 2 meters. So here, what happens, I put a radiant sphere here. That basically, if you look at there is a part that energy decouples from the source, that is my dipole, and then the rest part of it goes back to the source. Based on the Wheeler definition, he called it radiant sphere, that the radius of that sphere is lambda over 2 pi. This is what I put here. Basically, the diameter is lambda over pi. I basically scaled this here. You see that still there's some energy outside of this sphere that comes in to the dipole radiant sphere. So it's not exact border here. There's basically is some rough area that tells us outside of this we have radiation, and inside the energy goes back and forth between the antenna. So that's basically how radiation happens. Radiation happens when this energy decouples from the source and then travels with the speed of the light. Then we're going to talk about electrically a small antenna. So based on what we just saw and what Wheeler defined, it says that the antenna that is basically contained in the sphere with radius of lambda over 2 pi, we call that electrically small antenna. So the point here is, as you saw, the big amount of energy we are storing in this area that within the radiant sphere. And the radiated field here, that we have some power radiated from this. So what does that mean? It means that the quality factor of such a structure depends how small we have. We have a lot of energy here. That quality factor is going to be pretty high. Here, I'm going to go back to the Hertzian dipole. I'm going to write the equations. Theoretically, we can find this equation. This is very simple. With the simple integration, we get the electric field and magnetic field. So what I'm interested in these equations, again, very close to the dipole, I have 1 over kr to the power of 3. And when I go away, when kr gets very large, the part that is going to survive is 1 over kr in the electric field, 1 over kr in magnetic field. So I'm going to have only electric field in the theta and magnetic field in phi. But when I'm close to the antenna, very close to the antenna, I have electric field in both theta and phi. And then This part is important for me. 1 over k r to the power of 3. If you remember, when I showed you the static dipole, it was 1 over r to the power of 3. So it tells me when I'm very close to this dipole, I'm quasi-static. For this particular case that I have an electric dipole, I can model this antenna with a capacitor because it's mainly a stored electric energy. So that's the one I actually we're going to use. The other thing that I want to show here, I'm cross-producting this electric field and magnetic field to find the basically radiated power. So this is a Poynting vector. And I'm going to integrate this vector on the surface of the sphere with the radius of r. I want to see if I have a sphere with radius r, how much energy passes through that sphere and how much energy goes back and forth. So the real part of this SR basically is the term here, which is radiated power, and it is not function of distance. This power is going to travel with the speed of the light, and the density of the power is going to go down because of the sphere surface is going to go up. But when you integrate it, it's going to be constant. The interesting part here is the part that we have as imaginary part. So this imaginary part shows the power that goes back and forth on the surface of that sphere. And doesn't matter how close that sphere is to the center. We have this term that interact with the antenna. We have other source stored energy around the antenna, like this part. And these guys, they don't interact with the antenna because when I do the integration of this part, because of this sine 2 pi, and I integrate it with sine theta over 0 to pi, this term is going to be 0. This shows a standing wave between the two poles of the antenna, this north pole and south pole. So this is not going to interact with the antenna, and we're not going to consider it. If I use this term and I calculate the Q factor, I have 1 over KQ. So this is basically a quality factor that is slightly different from what Chu proved. And there are other one, McLean and everybody else did. So based on this simple logic, we know that quality factor is going to be KQ. So now I'm looking at this electrical small antenna with the radius R. We have few fundamental limits for this antenna. One of the limits is the quality factor. And the other fundamental limit is on the directivity, which actually I'm not right now talking about directivity. I'm just want to talk about the quality factor, which is 1 over KQ. So one point that I need to mention here is this 1 over KQ is for the time that antenna is not loaded. Basically, it's antenna by itself. And if I load the antenna and I match the antenna to something, this quality factor is going to be divided by 2. So we see a lot of paper published, and I made this antenna and I'm close to the Chu's limit. Actually, they compared their loaded Q with the loadless Q of this. So whatever they need to compare to, they have to compare with half of this, not the Q factor here. And actually, pretty much everybody compare with this, that is not correct. That theoretically is wrong. Then here I have electrically small antenna. I want to see what's going on with my antenna in terms of the current and loss. If I write the potential function, it directly comes out of Maxwell's equation in far field approximation. I have this integral. This part of the equation, which is not related to the antenna, the only part related to the antenna is this integral here. So if I want to see some field intensity at some particular distance in electric or magnetic, what I would need to do, I need to manipulate this integral. I have to have enough amount of whatever I have in this integral. So there are two ways to do this. I can increase the current if the volume of integration is very small, or I can make the volume of integration very large. The condition here is this R prime R with that particular direction of interest has to stay constant. So I'm going to add this current coherently. So that's basically what we do with arrays and large antennas. But for electrically small antenna, the volume is very small, means that I need to have a very strong current, either electric current or magnetic current. So if I have a loop, means the current is going to be extremely high, or if I have a dipole, I have a very high voltage. So you easily can calculate something. Like, for example, if your quality factor is 100, is actually a very good number, and your radiation resistance, for example, is like 1 ohm, and you want half a watt of transmitted power, you have 1 amp current on the antenna. And when the quality factor is 100, means the current goes to the resonator is 100 amp. So basically, you deliver 100 amp to the resonator, match antenna, to have half a watt radiation of that antenna. And I'm talking about really, it's not very small antenna when the quality factor is 100 and we have 1 ohm radiation resistance. If you go more aggressively, the current is going to go to 1,000 amp, and this voltage is going to go to 1,000 volts. Now, there are a lot of paper. Actually, I wrote a couple of them myself in 2011, 12, 13 at that time, that people, they say we violated the quality factor. So I would like to mention this. We have a quality factor here, which basically is about the second order systems, and they're cycling. They're oscillating with the frequency omega 0. This is angular frequency. So this is quality factor says the maximum stored energy divided with dissipated power multiplied by omega. This is thermodynamic definition of quality factor. What does that mean? It means there is no way you can break this. This quality factor cannot be violated. And it's easy to understand. Let's say, for example, somebody gives you $100 and it tells you per day you can spend or gain 10% on that $100. So after 3 days, you cannot come to $20 because the first day you're going to have $10 up or $10 down. The second day you have $9 up or $9 down. So maximum you're going to be like $81. You cannot come to like $20. Means you cannot change the stored energy very fast. Depends, this quality factor limited this. And that basically, when you look at the resonator response, this is magnitude of electric field or magnetic field. This is not power. So when I look at the signal, for example, a quality factor infinity means the signal goes straight. And here I have two different resonators, and doesn't matter what the frequency is. I count the number of cycles that is required for the magnitude of this signal to decay from 1 to basically 37% of the voltage that I have here. So we have 1 volt here. Here, when I go to 0.37 volt, I count this number, I multiply it with pi, that gives me the quality factor. So immediately you say if the quality factor from like 34 goes to 3.4, so basically after 1 cycle, my signal is going to die. This is what it tells you. So this is basically what I want you to have a feeling about the quality factor and how fast the energy dies. And there is a relationship between quality factor and bandwidth. The relationship that I have here is derived by Fano for an RL circuit. And it says that the quality factor is defined as pi divided by, the bandwidth, pi divided by Q divided by maximum of this log of 1 over gamma. And you see that this is not something constant. Depends what VSWR or what gamma you're talking about. The relationship between the bandwidth and quality factor is going to change. This is not a simple relationship. So here, based on what Fano showed here, I'm looking at the basically the return loss of a resonator, LC resonator, and I match that resonator to the match load, for example, 50 ohm. So at this point, I have 0 return loss, and then I have this bandwidth here. What Fano says this is not the best idea. So Fano says what? Says if you want to do this, that area better to invest it like this. So you don't make it perfectly match here. You keep your SWR around what you have, and then that is going to decide your quality factor here. you see Q time, I mean the bandwidth, Q times maximum of this. So the area of Q and gamma is going to give you the bandwidth. So to generate something like that, of course, you need to put a filter in front of the matching circuit, basically in front of your antenna with the infinite number of components. Here, I'm going to talk about the ESA that basically, based on what Fano says, the ESA is usually been modeled with RLC circuit. So I'm looking at the RLC circuit, and I'm showing you two examples here. One example, I'm matching that RLC circuit to 50 ohm, that at this particular, this is normalized frequency at 1, and this is return loss. So you see that at this point, I have minus infinity or 0 gamma, and it gives me, for this particular point, it gives me that much bandwidth. But if I increase my impedance instead of matching 50 ohm, I do it 96 ohm. So I don't have perfect match here, but my bandwidth for this particular gamma is increased. So this is basically what I call this zero order Fano matching. And I calculated this number versus gamma. Basically, R optimum is going to be R0 multiply this, 1 plus gamma squared divided by 1 minus gamma squared. And if I look at the bandwidth enhancement, you see that when the quality factor is, when the basically requirement for bandwidth is pretty low, like minus 20, you don't see much of the expansion, the variation here. And this number is going to be pretty much R0. But when I'm coming through a smaller number, like for example, minus 10, minus 5, or minus 3, if I go to minus 3, I can get 40% increase in my bandwidth without doing anything. I just put the R here. Instead of 50 ohm, I put 150 ohm. So you put the 1 plus half divided by 1 minus half multiplied by 50 is going to give you 150. So this is basically what I wanted you to know about the quality factor, bandwidth, radiation, and what we mean with the electrically small antenna. Now, I want to talk about the non-LTI antenna in the receive side. So for the receiver, we have a few options. One option here is that I'm talking about electric antenna, like this is like a small dipole. It can be a small, anything electric. If it was a small loop, I would have put the capacitor here. So these are dual. I don't need to repeat them for magnetic as well. So what I have here is, I have, for example, electric antenna. I match it with this j omega L, and I make sure that my real part of the impedance of the antenna is equal to this ZL. And imaginary part is basically is going to be conjugate of this imaginary part. And then I have perfect match. So this is what people they usually do. We have narrow bandwidth, the system is stable, and noise figure is very good, but the bandwidth is very small. The other one is if we add some loss here. This is some other people, they do this too. So if you have to have some bandwidth, you put some loss here. And then I increase the loss of the antenna with this loss, and that they will decrease the quality factor of antenna. And then I match it, and then I get some bandwidth. So I get wide bandwidth. This is a stable, but the noise performance is not good because of this loss. The other case here is I directly connect the antenna to load. For some cases, this load includes the entire receiver. I have LNA, I have everything here. Actually, for some cases, this is not that bad. It looks bad, but actually it's not that bad. You can get some bandwidth out of this. The last option I want to talk about is non-faster antenna. So this idea came out that, okay, if I compensate the imaginary part of the antenna and then put the matching, I can have a wide band. So I can get a wide bandwidth. The issue here is, for receive side at least, this is not a stable circuit. So it could go to oscillation. And the other problem here is poor noise performance. So basically the first, some of the papers that talk about the noise of the non-faster, they put the receiver down here with the noise figure like above 6. So basically the noise figure of the receiver was dominant, that the entire noise here. So we were not able to see the noise figure of this circuit. But if you put the low noise circuit here, like noise figure of 1, you will see that this example, that you don't have anything, it performs much better than non-positive. So that's so much for non-positive. So what we want to do, what we propose here is, we say, you know what, match the antenna through the how much bandwidth you want, and that bandwidth, that matching, you do the body Fano. So basically try to make that rectangle matching. And then we're gonna face the mismatch. So depends how much bandwidth you want, you wanna increase the mismatch to get that bandwidth. But what the mismatch does, mismatch will bounce back the energy out to air. So the antenna receives so much energy, so much power, and comes to the match load, to the mismatch, and like a big part of it irradiates. So then what I'm going to do here, I'm going to put the LNA right after this, and basically I have a wideband receiver. But that's not all. Let's see. This part that is Fano matching with the antenna, whatever signal comes in here with noise and with the distortion, this is going to bounce back. Not only the signal bounce back, the noise is going to bounce back too. The signal to noise ratio of the signal is going to stay intact. But of course, if I have a loss here, that loss is going to contribute to the basically noise figure of the signal. So this is what we did a few years ago with my student Pedram, is published in the magazine. So we do the mismatch here and we compensate with the LNA. Our suggestion was the LNA is a parametric amplifier. So if I have a parametric amplifier, I can absorb the matching in my amplifier. And also my amplifier has some properties that can be very low noise. So I'm gonna go through that here. Here, I'm connecting the antenna to the match load here. I have some R in and I have some quality factor. If the antenna is not connected to R in, so the antenna itself has this quality factor here, 1/2 pi f Ca Ra. And the best you can do with this, you can do a quality factor 2, right? Or 1/kaq. But if you add this R in here, you're gonna reduce the quality factor and you get bandwidth out of it. But the problem with this R in is gonna add noise to this system. What we propose here, we said we can put the R in, but this R in is not ohmic. It pretends to be low, but it is not low. And that actually increases the bandwidth here, but doesn't increase the noise. So that's the theory here. So parametric amplifier will provide that R in, and basically there's negligible impact on the noise. So this is basically the idea. So we have a Fano matching and the antenna, and this is my load here. So the red curve shows the antenna itself. Then I put the matching. For different matching, I have mismatch. So for the blue one, I have mismatch, this much. For the black one, I have this mismatch. So this is devious scale. If it was a linear scale, the area under black and blue are the same. But for the devious scale, we don't see. So then the dashed line is a design circuit, actually. For the black line, the solid line, you have to design an infinite number of reactive numbers to get that sharp edges. This is exactly similar to the future design. So you have, for example, some exactly like Chebyshev or something, we can design this circuit to have this performance. Then we're gonna put an amplifier here to compensate for that loss. So this is the way, the whole thing that we increase the bandwidth. But the key here is the whole reactive part is gonna be absorbed in this particular design. So now we're gonna talk about parametric amplifier. The parametric amplifier that we are interested is basically is the up converter. I want to talk about that. There is a difference between the transistor-based amplifier here and the parametric amplifier here. So the transistor-based, it uses DC source as a power source. Parametric amplifier uses AC source like pump. That basically is a major difference. And the other thing is when your signal comes out of this amplifier is the same frequency, basically a copy of the signal here multiplied with some coefficient. When you have up converter parametric amplifier, the frequency of this thing has changed. So for example, here I have 10 megahertz, here you have 100. So it depends how much gain you want. The other difference which is significant here is the transistor-based amplifier. No matter what you do, theoretically, you cannot make the noise figure of this amplifier zero. You always have noise. But when you go with the parametric amplifier, the source of amplification here is the nonlinearity of a reactive component. So like a voltage variable capacitor or current variable inductor. In theory, you can have this thing lossless. Of course, right, if you put a varactor, you have a series resistor, but theoretically, you can have losses. So theoretically, this parametric amplifier could be noise-free. Look at the parametric amplifier up converter here. So this is what basically it's going to look like. This part is my antenna and radiation resistance. And the reactive part of the antenna has been absorbed in this filter. So this filter here allows only the frequency related to the source to pass through this. Then I have something they call a pump, which is this is high voltage sinusoidal, which has its own filter that allows only this signal pass through, and I have my reactive component. So I have output signal, which I put the filter around this. This filter allows only the frequency around F0 to pass through, and this is my loop. So based on what, my signal is here, is a two-sided signal, like a real signal here. And then I up-convert it with this amplifier. What I will see here, when I pick up this part, Fs plus Fp, based on some form of equation, we call that the Manley-Roth series equation, we have some gain. And the gain theoretically maximizes with the ratio of this frequency, Fo, divided by Fs. So theoretically, if everything goes perfectly, the gain of this antenna, for example, you put 10 megahertz here, you put 100 megahertz here, you have a gain of 10. And basically, you don't have noise contribution from here. All right. So here, basically, we are doing this is the result simulation for a case that we have an antenna, a loop antenna, and it's connected to a matching circuit, a parametric amplifier. And here we show that with the different value of M, we can change a different value or L is connected to the other side of the amplifier. We can add this resistor, this is Rin, we can add this to the resistor of the antenna itself, and we can increase the bandwidth. So the price we are paying when you make this R larger, the gain that your amplifier gives you goes lower and lower. So here I have the gain equal to 0. Basically, I'm just compensating for the antenna loss, and this is the bandwidth I get out of this. So original bandwidth, for example, was 1.1 here, and now here you get 5 megahertz. So it depends how you design this, we're going to get a different bandwidth. Actually, this 1.1 megahertz is not the antenna that they're using. The bandwidth is 550 kilohertz. Here, the curve shows that basically when RL, this one, will change, how much basically the gain bandwidth will shift here. So we can go all the way to gain bandwidth more than 30. And of course, if I bring my gain 1, the bandwidth is going to be 30 times larger. For the case that basically A is the one that is the other side of the parametric amplifier, and this RS is basically a function of that RA. So here's some simulation for one particular case. This is the load that we had here. So we match it, and we put the amplifier before this, and we see that we have a pretty wide bandwidth here. And then we have the gain around 0. So we use here some parametric amplifier with black and some regular amplifier with red. And the bandwidth side, you see that these two amplifiers, they are the same in terms of the bandwidth. So that amplification, any amplifier can do. But when you go to noise performance, the red one is parametric amplifier, and these three curves, they are an amplifier with different noise figure. So if the noise figure is equal to 1, your noise, overall noise of the system is going to go up here. If noise figure of that amplifier is 0.75, you're here, and noise figure is 0.5, the 0.5 noise figure of your amplifier, you're going to give you this green one. And 0.5 noise figure is pretty good, actually. So this parametric amplifier has 2.9 dB better performance than the best amplifier you can put there. So you see that there is a value, big value here to use parametric amplifier. So this is what basically FedRAMP design and manufacture. So this is loop antenna with a radius of 93. We have all sorts of filters and input and pump. And the pump is 2.19 megahertz. The frequency of the antenna is 100 megahertz. And our goal here is go from 92 to 108. And this basically 2.1 gigahertz potential is going to give me 20 times gain. So these are the connection of a spectrum analyzer, pump, and signal, and then the receiver. Here it shows when we change the trading between the gain and bandwidth. So the antenna was 550 megahertz bandwidth. Here, for 0 dB gain, I can get 10 megahertz bandwidth out of it. And here I can show you, this is the regular antenna. We match it with the 50 ohm. We did a matching circuit here. So this is some matching that I call that the electrical coupled loop antenna, something like that. So we can do the matching here, and this gave us that particular bandwidth for 10 dB. So here, basically, we are looking at the variation of this curve versus the bias, and this is the overall example that we have for the antenna. This is receiver here, and the resistance I see this time is going to be that ZRS, and I'm absorbing the reactive part of the antenna. So this pretty much was what I wanted to talk about the receiver. So we mismatched the antenna, but there is a smart way to have that mismatch. We designed the mismatch, and then we put the parametric amplifier right after that, and we can receive the wideband signal with the low noise performance. Now, I want to talk a little bit about the non-LTI antennas in transmit side. So remember that that charge particle that I show you when the couple of charges they get away from each other come back. I'm going to use that here. So the criteria that we have, so the antenna is much smaller than the radiosphere, and then the antenna is able to tolerate really high voltage or high current. Depends if it's going to be reactive part is electric or magnetic. We're going to be able to tolerate extremely large current or voltage, and high radiation efficiency. The receive side, the trade-off is between the bandwidth and noise figure. So basically the trade-off between the criteria for receive antenna and transmit antenna, they are slightly different. Here, noise is important for us, and here, basically, efficiency is important for us. So let's look at the first order antenna as a first order system. So if this is an electric antenna, I claim that it's going to be a capacitor. If it's a magnetic antenna, I claim that's going to be a loop. So when I match it, when I put the tank next to it, tune it to some frequency, the normalized edge doesn't matter. It's going to be electric or magnetic. I'm talking about impedance or admittance. It's going to have some form like this. And this is normalized to resonant frequency. So omega equal 1 is resonant frequency of this. So when omega goes really, really small, my h omega is going to be j omega, my transfer function is going to be j omega divided by q. So if this is a capacitor, here I'm going to, if the electric antenna, this is going to be admittance, I'm going to have a capacitor. If it is magnetic antenna, this is going to be a real positive, and I'm going to have inductance. No matter what, I can model that circuit with the RC or LC. Then the tuning part is going to be either C or R. So, and we can demonstrate that basically we did actually for Hertzian diode. So again, no matter what we do with the electrically small antenna, we either have a leaky inductor tuned to a capacitor. So this is tuned antenna. So we have a tuning circuit with capacitor with connected to inductor. Or we have leaky capacitor connected to the inductor here. So that this inductor is my lump element that tune this. Or I have a leaky capacitor connected to leaky inductor. I have an example for all three of them. So here, for example, this is a regular loop. Here, electric antenna could be PFA, could be patch, could be monopole, dipole, everything. These are all electric. And the last one here, this is the antenna that I have. I brought the inductor, matching inductor, inside the radiation structure. So both electric and magnetic energy, they radiate. So theoretically, the quality factor of this type of antenna is going to be half of the quality factor of the just electric, just magnetic. So because both energy, they're radiating. So this is it has a self-resonance at any frequency that you design. These two, this guy, monopole and loop, you have to have a tuning element to match them. So there is another thing that we need to know, that let's say my electrically small antenna, we just realized that is going to be a tank. I can make a series model or parallel model, that doesn't matter. I'm going to have RLC in my model somehow in some form. So if this is my tank here, and I put the voltage source on this tank with some resonant frequency, and I turn my voltage source off, the voltage across this system decays with the quality factor that this tank has. So we cannot violate that. This is going to decay. So who is governing the bandwidth? As still this this tank is governing the bandwidth. You cannot do anything about this. So you can see a lot of paper published between the 90s and 2010 to 2013 that basically that's what they're doing. They're switching the tank and they're trying to basically increase the bandwidth of antenna. You cannot do that. What we need to do, we need to break the resonance here, the way that basically you bring the charge away from each other and you keep them there, you don't move them. For that sense, I'm going to use the model as basically a resonance circuit. Here, I'm going to give you an idea, something that you can test yourself. So let's say I have a pendulum. This is a second order system. I have two types of energy for second order. For electrical resonator, we have electric energy stored in capacitor, magnetic energy in inductor, and these two energy, they're going back and forth, each half a cycle. For pendulum here, I have kinetic energy and potential energy. That over here I have maximum kinetic energy, over here I have maximum potential energy. And that exchange gives me resonance. So this is what I have. And the frequency is decided with the length of this pendulum. So if I consider this as my resonant structure, what I can do here, I can change the parameter of this resonator, like L, and change the frequency. What I'm going to do here is, I'm going to, in some point of oscillation, I'm going to nail this point down, and then I'm going to change the resonance. The resonance this time is going to be LB divided by G, and the frequency is going to go higher. But what I'm doing here, I have to do it in the right time. The right time that I'm doing this is basically is before the pendulum hit the surface, hit the point here. So I have this curve here for different time. So I have the velocity of the pendulum. I have electric, magnetic, and potential energy and kinetic energy curve here. You see that I can easily have a FSK modulation here by changing the length of this resonator. I can change the omega. We're going to use pretty much the same idea. So this basically gives you the frequency modulation. I can have amplitude modulation. How? When the pendulum comes up here, I just hold it. I don't let it go. I keep it right here. And basically, what I have, I can keep this as long as I want and then let it oscillate again. What is give me? It gives me a cycle here, and then it gives me a steady here, a cycle and steady. I can make ASK out of this oscillator based on the way that I stop the oscillation. And here I have basically, again, velocity, kinetic energy, and the potential energy, kinetic energy. And here is the modulator. So we're going to use some of these ideas to see if we can modulate the antenna. Now, here is basically one electric antenna. It could be monopole, could be dipole. And what I have here, this source for time being considered, this is a battery. So there is a battery here. There is a low pass filter here. But this low pass filter, the last element has to be capacitor. Whatever I have here has to be capacitor. So I have this L and I have this short circuit. So the battery, I short circuit this. When I short circuit this, the current goes through the L2. And then when I open it, a static current through the L2 is going to go to this capacitor, which is my antenna. And there is going to be a resonance between these two, because this is pretty much what Hertz do. So the resonance is going to happen here between L2 and antenna. And as long as this switch is off, this guy resonant, but it's going to be a damped sinusoidal because antenna is going to spend some of that energy. But the time that I turn this guy up and on and off, there's a critical point that I need to turn this on and off. And that critical point is when the voltage is equal to 0, means energy inside the antenna is 0, and the entire energy is in L2, I can short circuit this. And I can keep it short as long as I want and then make it short and basically open. This source here won't see what's happening here. So you have a battery and you see a resistive load here, which is basically energy that you're spending here. But if you want to manipulate the magnitude of ASK, you can have a sinusoidal or so you can put some information here. As long as the frequency of this information is lower than this low pass filter, you can pass through the filter and you can manipulate the antenna. But whatever frequency I have here is not going to come back to the source. So here I show you one example of ASK. This basically, I simulated the dipole, which basically here I have time versus a microsecond. And the dipole frequency, like for example, is like 100 times smaller than resonant frequency. I'm going really, really low in the frequency here. And then I'm do the full wave analysis of the antenna here, bring it to the AS, basically, this is ADS. And then I'm doing this. My low pass filter here is just this capacitor. So I put a large capacitor here. I didn't even design this because I'm going to use battery. The battery doesn't care if I have inductor here or not. So the capacitor will do the job. So this inductor and this antenna, they do the resonance. And you see that this thing perfectly works. I have other model here. I have inductor with two switches here. I have a switch that short circuited inductor from this side, or I can leave this open at the same time short circuit the inductor from the other side. So I can have, when this L is short circuit to this, the antenna is at rest, so no radiation. When I open it up and short circuit here, there is an oscillation between these two. And I can control the time that basically I'm doing the switching. Happens when the voltage is equal to 0. Again, this source is a battery for time being, but it can be basically a time variant signal. I can do this example here. Instead of having a no inductor here, I can put another inductor here. And when I short circuit here, I still have the resonance between L1 and antenna. When I open it, I have a resonance between L1 and L2 antenna. It's going to give me FSK. You can see the FSK here. I have the same model here, same dipole here, and then I have this two inductor that gives me two different frequencies here. And I have another version of this basically frequency shifting, and basically it uses two switches. There are a little bit difference between the sophistication of the switches between these two, but the point here is the timing between the switching is extremely important. It has to be timed exactly when the voltage is equal to 0 here. And I have a lot of more of this collection of this different modulation. We don't have time here now. So I don't know if Chris, we have time to basically go to entertain some question here or not.